Welcome to a lesson with Dr. Powell. Let's take a look at cylindrical coordinates and spherical coordinates and how we can work with transformations with them and derivatives. For instance, what if we have a function fx, fxyz, and let's just make it fairly straightforward, simple. What if we did something like x plus y? And what if we're interested in knowing what the partials of f are with respect to these different coordinates? So let's talk about what these coordinates are. First, cylindrical. It's basically just polar in the x and y, so r and theta here, and then we just add in an altitude z. So in order, r theta z is what we get. Okay, so let's just focus on that for a minute. How do you convert? Well, if you just look at a little picture, think x and y, theta and r. If r were 1, then y would be sine theta. But by similar triangles, we multiplied all the sides by r. So this is just r sine theta. This is r cosine theta. So basically what we have is we take f and we compose it with kind of this thing here where we set x equal to y equal to z equal to something. Z will just be itself, it's still altitude. X will be r cosine theta, and y will be r sine theta. Okay, so if we were to take a derivative, we take the derivative of f, which is 1, 1, 0. Then we take the derivative of this transformation. Notice how we have 3 outputs, so it'll be 3 rows. And we have 3 inputs, r, theta, and z, so we have 3 columns. So it's really a 3 by 3 matrix. So how do we get it? Well, we just take this column and we take the derivative with respect to r, then theta, then z in different columns. So with respect to r, we'd have cosine theta, sine theta, 0. With respect to theta, we'd have negative r sine theta, r cosine theta, and 0. With respect to z, 0, 0, 1. So to just multiply these out, and we end up getting, so we have a dot product of this and this for the first entry. Because really what we're after here, when we compose this, is we're getting a matrix, which is the derivative of f. This will be the derivative of f with respect to r, theta, and z. This guy right here is the derivative with respect to x, y, z, and we just calculated it right here. Now, this derivative with respect to r, theta, and z will simply just be, we could think of it as the partial with respect to r, theta, and z. So these partials will pop out right in the matrix itself. So we'll actually see what they are. So let's see. So we take this dot product with that. We just end up getting cosine theta plus sine theta. Okay. And then the next one, we get negative r sine theta plus r cosine theta. And the next one, we just get 0. Okay, so that's what we have. This right here is are the partials. This is the partial respect to r, respect to theta, respect to z, pretty much as probably we expected. Okay, now let's keep on going. And let's suppose that we want to further compose this with a conversion from cylindrical, r, theta, and z, and keep going here and do something else. We're going to put it into spherical. So let's talk about what spherical is. So looking at this picture that we have, you notice how we have z and r. So imagine that we do something kind of polar with like z and r. Z and r are not 90 degrees from each other. And if you kind of turn it, so r is facing upward, say, and okay, so imagine you have z and r, right? And so you kind of turn it so r is up and z is down. You're going to get a picture that looks something like this. So r's up and z's down. And then this part right here, that's coming right here, you can imagine it being right here. Okay, so that line, you can imagine this after kind of a rotation and maybe even putting this z-dill right over here and then kind of flipping over. You have something like this. This distance to the origin to that point we'll call rho. Okay, so that's going to be rho. And then we're going to call this right here an angle. We'll call it phi. And phi is actually visualized in space, let's see, right here, as the angle that's made with the positive z-axis. Okay, so rho is right there, and phi is that angle right there. So the conversion here is the same as you do for polar here. You're thinking of z as being this right here, and that's going, z is going to be equal to simply just rho times the cosine of phi. And r will be rho times the sine of phi, and theta is just itself. Okay, so we're going to look at that. So for that, so we have a composition here, then we have another multiplication keep on to get to, so we can actually, and the resulting matrix will actually be f rho, f theta, and f phi. So we'll actually see what these partials are in just doing this multiplication. Okay, so let's do that. Okay, so in this multiplication, we would end up having okay, so we take this and take a derivative with respect to, so our variables in order are actually rho, theta, and phi here. So you can kind of think about that right here. We have rho, theta, and phi. So with respect to rho, gives us sine phi, 0, and cosine phi. With respect to theta, we have 0, 1, 0. With respect to phi, we have rho cosine phi, and 0, and negative rho sine phi. Okay, so we take this matrix and multiply it to all this. Now we already multiplied all this together. It was this. So we're really just multiplying this and this together. So in doing that, I'll put the result right at the top. Then we'll be able to pick out what those partials are. So the result would be just taking the dot product of this with this. And so we end up getting cosine theta plus sine theta times sine phi, and the rest is just zeros. Okay, right there. Okay. And the next one, we end up just getting that negative r sine theta plus r cosine theta. Okay, and then for the last guy, we take this and this, we end up getting, and I'll just write it right here, rho cosine phi, just let's see, times that, right? And that's everything that's non-zero. Okay, so cosine theta plus sine theta. Okay, so as a matrix, so this part right here is f rho. This part right here is f theta, and this part right here is f phi. Now, keep in mind, notice that there's a little bit of an issue because we have, let's see, or is there? Maybe we're good. Okay, no, we have r's. You see how we have r's right here? So we have this r and this r. Now r is not really, is a cylindrical coordinate thing, so we have to like rewrite r. We have to use this substitution to get it in terms of rho and phi. So if we ever have to make substitutions here, we do that. We need to do that so we have this completely in terms of in spherical coordinates. But after doing that, we should be good. And that is, and then we have our partials, and we've just successfully taken the derivative of this simple formula in Cartesian coordinates, and took in the partials with respect to spherical coordinates. Thanks for watching.